Good morning. Welcome back to the second day of the breakout sessions at the PDC. I'm just amazed how many people are here. This is staggering. I'm out of just pure curiosity. How many of you actually went to the talk yesterday too? Okay. Welcome back. My name is Jim Miller. I'm the lead program manager on the Runtime kernel team of the Common Language Runtime. And I want to tell you a little bit about its architecture. And I want to apologize for the pillars in the middle of the room. I like to look at everybody, and it isn't going to be possible. So I'm going to start the talk, sort of the outline of the talk. I'm going to talk a bit about where the Common Language Runtime fits in the overall view of the .NET framework, and in fact of the entire .NET platform, just to give you an understanding of where the bit we're diving into fits. Then to talk about the goals. I did mention this yesterday also. My team has been working on this project for 2.5 to 3 years. I've been working on it personally for a little over 2. This is the first time we've been able to talk about it in public, so we are absolutely excited about that opportunity. If you find any of us, feel free to corner us. We left 75-degree weather and clear, cloudless skies with beautiful views of Mount Rainier to come somewhere else, and that was to meet with you. So thank you for coming too. And really, just stop us anywhere and ask anything you want. We are just dying to tell you. This particular track, the ones with the 3 in it, is the infrastructure track. And it really concentrates on sort of the insides of this whole system. Anything that we can, we want to let you know. We want you to understand. We want you to participate and tell us what you think, where we've got problems, where you like it. Just really, really, really take advantage of it. That's why we're here. So anyway, after we tell you why we've been doing this for 3 years and what we hope you will get out of it, I want to sort of dive into how this runtime is used. The name runtime is a little misleading, at least to me. When I think runtime, I think the Fortran runtime, which is the granddaddy of them all, the COBOL runtime, the C runtime, the VB runtime. They're all there when you run your program. That's what they're there for. This runtime is much more pervasive than that. It's available throughout the software development cycle. So we'll talk about how this runtime is used at design time and compile time, and then at deployment time, and then finally at execution time, and then summary, and then there'll be plenty of time for questions. So where we are, if you were here on the first day of the general sessions, you'll recognize this slide. John Shushuk presented this, and it's the entire .NET platform. And as you can see, the framework is sort of a small piece in the middle. That's what we're going to concentrate on in this talk. If you think of the first day's sessions as at about 26,000 feet, this talk is going to dive us down to about 10,000 feet. In this track, there are 6 broad talks that are at that level. Some of them have gone by. Some of them are still to come. The other 9 are really dive downs. They go down to 5,000 feet. So the broad overview ones, just so you know, there's one, this architecture overview. There's one about this platform from a COM programmer's perspective. I think that one was yesterday. I gave one yesterday on language integration. There's one, I believe, still to come on security, one on deployment and administration, and one that I know is later today. In fact, it's the next session on the overview of the base class libraries. So those 6 are to give you the wide overview of everything that's in the framework. And then the other 9 in this track are sort of deep on a particular topic. The framework itself is sort of part of that core piece. And it's divided up more or less like this. At the bottom is the Common Language Runtime, which provides the services for everything else you saw in the demos yesterday and the day before. On top of that, the base class library. And on top of that, data access, XML, parsing and unparsing. Then web services. That's sort of the big theme, how you make your websites accessible to others for reuse and how you reuse others. And then the user interface, and we really provide two different user interface paradigms, one of which is the WinForms, which is the client side, and one of which is called WebForms, which is server side, and there are plenty of talks on those throughout the conference. The place I've been living for just over 2 years now is in the Common Language Runtime. In fact, sort of at the bottom of the Common Language Runtime. The structure of the runtime, there's a class loader and a class layout engine. The job of the class loader is to find the pieces of the program that are needed to run it, load them into the memory. The class layout engine's job is to figure out the shape of all the objects and the shape of the descriptions of all the classes. That's sort of the basic thing you need to get up and ready to go. On top of that, there's an automatic memory management system called the garbage collector. There's some stack walking code, which lets you, while your program is running, it lets us look at the stack to see what things are being run. A code manager, which I talk a little bit about later. That's all the very lowest layer basics of this whole platform. Then on top of that, we have three major groupings of code. One is we have a set of compilers from a special intermediate language, which we've defined, and which all of the compilers that you've seen that run on top of the runtime generate that IL. And there are now about 15 different languages that are up and running and generating that IL. Some from Microsoft, most of them from other parties, some from companies, ISVs, some from research universities. They all generate the IL, and we have compilers that take that IL and turn it into native code for the machine that we're running on. Then there's execution support, which is really what most people think of as a runtime. It's the stuff you need to do while your program's running that was too complicated for the compiler to put right in the binary code itself. So in our case, it's things like if you're on a 32-bit machine and you want to multiply two 64-bit integers and you don't happen to have that as an instruction in the hardware, then we provide a little procedure there to call that does that work for you. That kind of thing. Allocating memory is in that execution support, and so on. Then there's a security system. It's a very, very flexible, evidence-based security system. Its roots go back to, it's really a trust management system. Its roots go back to some work that was done at AT&T Labs probably about 5 or 6 years ago now, and then it moved over when I was at the World Wide Web Consortium. We joined with AT&T Labs. We did some joint work on trust management. And then Microsoft has adopted that basic strategy and that basic technology, and that's really what our security system is based on. There's a talk on that. I think that's later today. And on top of all of that, the base class libraries. Base class libraries to me are things like the definition of an object, the definition of a string, definition of arrays, delegates, the very basic things you have to program, delegates, stuff like that. And then on top of that, there's this big framework thing, and I've never actually really worked with or on that framework directly, but that's actually where most of the user value is in the framework. But this talk is about the infrastructure and what's at the bottom of that whole stack. So what's the runtime and what were we trying to accomplish? And why is it important? So the big ticket item here, simplify development. We think that developing large applications of any kind, and especially large web applications, is just far too difficult. And we feel that you can't do it by just layering on top of existing things. You need to build right down to the core of what you're doing some very high-powered assistance to make that development easier. And we've taken really 3 separate attacks on that. So the first is we really want people to write less code and reuse more code. So we provide a very broad and consistent framework that contains a lot of reusable code. Think of it as taking all of the Win32 APIs and reorganizing them so that they're easy to find, and then making it so that you could take one, modify its behavior a little bit, and use it yourself. So reusable code on top, as well as maintaining what we've had for years with COM, which is interfaces. We still believe that those are extremely important. If you have two large components that want to work with each other, they really need to communicate by a very well specified, clean interface. That really is the right way to do the programming in the large. We haven't changed that at all. But what we've done is we've decided to concentrate as well on the building of the components. And we've said there, this reuse that you get through the object-oriented style of programming really is critical. It really is the key to productivity. So we've added that as well. Second major step, really important, is the plumbing disappears. I don't mean that we hide the plumbing. I mean it's not there. It's there to me because I have to build it. But once I've built it, you don't have to worry about it. You just use it. It's completely invisible. So the main things that enable that, the major single thing, is metadata. What I mean by that is every single thing you build in this system is self-describing. So when you build a type, all the information about that type is provided along with it, packaged with it. It doesn't travel separately. It travels in the same XC or DLL that the code for that type travels in. And it has the name of the type, the name of its base class, all the interfaces it implements, the names of all its members, the names of all its methods, its fields. Everything that you need to know about that class is available along with it. It's not just a raw lump of code. Right? That means that our tools can look at those descriptions and help you understand what's going on, help you build with it. You get things like IntelliSense that can tell you what type names are available, tell you what field names are available, what methods, and so forth. Really powerful, and you'll see that as a long theme through this talk and a number of the other talks is metadata, metadata, metadata. What is it? It's a self-description. Right? Second big thing, if you've ever done any work where you're trying to work across processes or across machines, it's what we call remoting. There's a real problem about who builds all that infrastructure and the proxies and the marshalling stubs and all the rest of that. That's a very hard problem. It's been a pain in the neck to do for years. Now, all you do is you say new. You say new on an object. If that object has been defined as being remote, we will build a transparent proxy for you. It looks just like the object you want, except that whenever you access any of its fields or call any of its methods, it's transparent to you, turned into a call across the network or across the machine to the actual object. The work is done. The results are returned back to you, all invisible. You don't have to write any of that code yourself. Thank you. The third major piece is the memory management. You still have to allocate your objects, but you do it by saying new. So you just say new. We will allocate the space and initialize it for you. And that's it. You don't have to reference count it. You don't have to release it. You can if you want. If you know you're done with it, you might want to close it so that you release resources that it's using, but you don't have to. And you certainly don't have to release the memory because the garbage collector will take care of that for you. That means no dangling pointers, no null pointer references, no problem where you've got a cyclic data structure and you release every piece of it and the whole thing still stays around. It's all gone. It's all taken care of for you automatically. Just allocate it. When you don't have any more references, it goes away. And finally, this is really the biggest thing. And actually, I need to say this is the biggest thing, but it's actually not part of the common language runtime. But it's the critical thing about the .NET platform. We have really great tools support for everything. It's built on what you already know in MS Dev, but it goes the next step further, and it integrates all of this stuff directly into it. So all the designers and wizards, all the debuggers, all the profilers, all of that stuff right in the same box all at once. That's what makes the whole development process easier. So what do you get out of that? That's all designed to give tremendously improved productivity. And internally, we have seen that productivity gain. We'd love to know when you get home, get those bits installed and try it out. Tell us whether you see productivity gains. We certainly do. People have reported factor of 2 performance, their productivity gains in internal Microsoft products. Second major goal, simpler and safer deployment. It's the problem we've heard about over and over and over again. We felt the pain. We want to really work on that problem. So what do we do to fix it? First thing is there is no registration required, zero impact of an installation. If you want to take an application and deploy it, just copy the pieces. That's all you have to do. If you don't want to do that, just copy the one piece that's the self-description of it, and as you run, we will incrementally load the pieces that are needed as you need them. Thank you. Second thing, really important, side-by-side versioning of shared components. How often have you had some component, let's say the grid control, that two applications want to use? Right? So you've got these two applications and the grid control, and they both want that grid control. And you install the new version of the grid control, and guess what? It works with this one, and you need it because it's much better and it does what you want, and that application breaks. Right? That's not going to happen anymore. You can have that same shared component in multiple versions on the machine, even in the same process, and two applications can pick two different versions of that same shared component. It's really neat. How do you do it? When you compile your application, we capture all the dependencies. So when you compile it, we know what version of the grid control each of those applications was compiled with. And then there's administrative controls that allow you to say, for each application, use the one it was compiled against, or use the latest compatible one, or use the latest known good version, and it's independent. So this app on the same machine, that app on the same machine could be picking two different versions of the same shared component. And the third thing with deployment, evidence-based security policy. The best way to explain what problem this solves is to just say, I love you, I love you, I love you. It's not going to happen again. It just isn't. The way it works, when we load a file, we know where it came from, we know who produced it, and security permissions can be given on a very fine-grained basis based on any evidence that you like. So the ability to send mail is not going to be granted to any arbitrary program that comes down the wire. The security policy is not just about who's running the program, it's about what program they're running, and not only what program they're running, but what components they're running, and not only what components they're running, but if there's a call to send mail from this procedure, that procedure has to have permission to send the mail, and so does the guy who called it, and the guy who called it, and the guy who called it, all the way up the call stack. And no, it's not as expensive as you might think. So the key to this whole security policy is you get to make decisions based on not just who's running the program, but also all kinds of information about that program itself. That's what you get. The end of DLL hell. Third major goal, scalability. We really want this system to go all the way from smart devices at one end up to web farms at the other. The smart devices part, there's a separate talk on. That work is just getting underway. Well, it's underway quite a bit right now. And there's a good talk about that I believe is coming this afternoon. Unfortunately, I don't know the name of that talk. It's listed at the end here. So if you want to know more about the smart devices story, there is a really very good talk about that. The bits that you have today don't include that. They include everything from effectively the desktop to the web farm, but we plan to go down to the smart device end as well. Another piece of that scalability story is the automatic memory management. That memory manager is just amazing. It's self-configuring and dynamically tuning. What do I mean by that? You just start up, and it knows whether it's currently running on a single processor or multiprocessor. If it's multiprocessor, it will use all the processors in order to manage the memory, and it will manage memory based on physical locality, number of other parameters. As it's running along, if memory pressure increases, because your program suddenly is using more memory in a unit time, it will modify the way it does its management, and it will change over time. We've tried a very large number of strategies, including ones where users could control the memory management system. What we've discovered in every case is this thing just outperforms any kind of configurable system we could come up with. So we've made it self-configuring. It just looks at the parameters and is continually tuning itself for best performance. And it comes in two flavors. There's a flavor that's tuned for servers, essentially, which gives you very, very high throughput. And there's one that's tuned for interactive use, which gives very low pauses, although its throughput is a little less. So in fact, it scales across a very, very wide range. We've also adopted thread pooling technology. So instead of creating some fixed number of threads and allocating them to a particular application for its use, whenever an application needs a thread, it goes to the pool, it grabs it, the thread runs. When it's done, it goes back to the pool, and it could be grabbed out of the pool by another application the next moment. That also dramatically increases the scalability, and those pools are done correctly for the multiprocessor case so that it knows about thread locality and so forth. Another big thing, I remember I told you about that remoting story where we make the transparent proxies, and automatically you just knew it and it's just there. We support, in addition to what you would consider sort of the normal paradigm of a remote procedure call, where this guy wants some work done on that object, so he tells that object to go and do the work, waits for the work to get done and gets the answer and has to be idle that whole time. We also provide asynchronous, where I tell it to start working and I get back something that I can use later, so I go on doing my working. And whenever I care to see about it, I can say, okay, are you done yet? If not, let me wait. And if so, tell me what the answer was. We also provide what some people call eventing and some people call fire and forget, which is a kind where this guy's running along and just wants to say some event happened and just sends a message out to that guy and just keeps going and doesn't want an answer, doesn't care about the answer, and just keeps going. So all three models are supported in that same remote proxy configuration. And the smart device version, and this is really all I'm going to be saying about it. As I say, there's a separate long talk about this. It is designed from scratch to run on multiple real-time operating systems, and it will leverage exactly the same tool set that's used for the desktop and the web farm. So all of the Dev Studio things you're seeing, all of the debugger, all of the drag and drop controls, all of that stuff will be available in the small device version as well. What do you get? Better performance, less cost. Next major goal, we want to support both very rich web clients as well as very safe hosting on the web. And so those are really two things. I sort of jammed them on the slide because I wanted to save slides here. But that means we provide an entire user interface package for your use on the client. That's WinForms. That's for what you use for doing ordinary apps running on your client. Also works, of course, if you're doing a browser, whatever. It's the client-side controls. We also provide ASP Plus web forms, which are controls that can run on the server. And you've seen a lot of that, and there have been some very good talks, and there's an entire track devoted to those two interface paradigms. And I strongly urge you to go to some of those talks. That stuff is really just amazing. The third thing, I keep harping on it because it happens to be one of my pets, which is the security stuff. Code is granted permissions. The whole model here is that there's some evidence that's collected. There's a policy on the machine or the application that's administratively set, and that policy says, given all that evidence about this program, what permissions do I let it have? And the evidence includes who the person is running it, what the program is, where the program came from, who signed it. Anything else that might be of interest is just fed into this policy, and the policy is all configurable. We ship standard policies, several of them, and so forth. Now, you have to put that all together. And so there's what there's a little bit of a confusion because when I say safe web hosting, I mean probably exactly what you think, which is I want to be in the business of running a website that hosts other people's code. That is exactly what I mean. There's unfortunately a conflict of terminology. We call the host environment is that application that starts our runtime up. So for just a minute, I'm going to use that term. So whoever starts up the runtime, which we call the runtime host, and that could be things like Internet Explorer 5.5 that was announced yesterday. It could be things like Information Server, IIS. SQL Server will be hosting us. The shell. You can write programs that host us. All those hosting APIs are defined in the bits you got yesterday. Whoever starts up the runtime plays a very special role in the security policy. They can do three things, really. The first is they provide some evidence themselves. So part of what happens is when we need to load a class that we haven't seen before, if we can't find it in sort of the obvious places where we normally look, we go to the host that started us and say, would you please find this? And when it finds it, it also tells us where it came from and information about the thing that it just gave us. So it is part of the evidence supplying machinery. It also, interestingly enough, it has the power to say, I want to alter the security policy, but only by making it more restrictive. So if there's a machine-wide policy, the host can say, well, that's fine and dandy, but I'm being more restrictive, and you can't grant that permission, even though if you've been running on some other host on this machine, you might be able to do that, but not inside me. So that's things like SQL Server use that to make that environment absolutely safe. And then the final thing that the hosting program does is it is the one that decides if I'm on a machine, I have lots of applications and lots of processes. It's the hosting application that figures out when to create processes and which applications to run in which processes. And it can decide to run several applications in one process, or always run every application in another process, or run this application in this process even if 6 people want to use it, make 6 copies of that application over here, and make 3 copies of a different application over here. All that's decided by the hosting environment, so that's no restrictions from the runtime point of view, but there's a support for pretty much any way you'd like to configure it. So whoever starts up the runtime has an awful lot of control, and that's why ASP Plus has its own rules for running the runtime, and SQL Server has different ones, and they're both able to use the same runtime base. So this whole thing is to get at having robust applications. Another thing that the runtime does is it's converging a number of different programming models. There's been a COM programming model that you're very used to, and it's a very useful one. And there's an ASP programming model that you're used to, and it's a very useful one, and it's not the same as the COM one. And boy, do I wish I could say there was one data access story, but I can't say that with a straight face. So there have been at least 3 different programming models, and they're really different, and you really had to learn all of them to do anything. So I can't say we solved it. I wish I could say we solved it, but we've taken the first major step forward. And the rules, the ground rules on that engagement were everything you can do today, you can do in the common language runtime. 100% of it, all of it, in exactly the way you're used to. So if you wanted to use COM programming, you can do it. If you want to use ASP programming, you can do it. And if you want to use our current data access stores, you can do it. In addition, we have made, using the frameworks, a consistent way to do all of that that's designed to be easy to use, extremely scalable, and have one consistent API across the whole thing. So it's that big framework that's on top of the runtime that raises the level of programming abstraction and lets all of that take place. The other thing that you get from that that's easy to overlook, but it's tremendously important in practice, is today we have a bunch of tools that make doing the simple tasks really easy. And there's just no question that's unbelievably valuable, and we're not going to lose that. But today, you're given a stark choice. Use the tools that make it easy. And if you want to do anything more than what they were designed to do, if you want to get any more of the power of the programming model, throw it away, learn to do it the hard way, and do it that way, okay? You guys know that's not very good. We know it's not very good. We've finally done something about it. So what we do is you have this hierarchy in the class library, and if you think about it, if you stay to the bottom of the class library, the most derived classes, those are designed to be very, very, very easy to use, at least as easy as the best we had before. So that's all still there. But now if you need a little more power, instead of going straight to the metal, just go up one level in the hierarchy and see how those were built. They were built out of other building blocks, which were easy to use, but not as easy to use, and were more powerful. So just go up one level in the hierarchy. And if that's not enough, go up and up and up, and eventually you'll come to a point where it's what you're used to be doing, and then you've got the full power of what you used to be doing in the way you used to be doing it. But it's a very gradual thing. So this one I think is really key, and what do you get from it? You get much less training costs, easier to train people because you can do it incrementally. And again, that leads to tremendously higher productivity. And then finally, and we've been saying this, it's sort of funny, this has been my theme song for 2.5 years, but even I'm getting tired of hearing it at this conference already. Multiple languages. We have a common type system. It's object-oriented in flavor, so it has classes and methods and fields and all that sort of stuff. It also supports procedural languages. Procedural languages, things like C and COBOL, that don't originally have object-oriented flavor to them. And functional languages are possible too. And if there was a languages panel on Tuesday night, and there's a whole track 5 is all about third-party languages. And if you go to the exhibit hall, you'll see a number of languages. It's really a very wide set of programming languages that are supported. Now, on top of that, and this is really key, what use is it to have all the programming languages running if they can't use that framework? Why would we invest so much in making a framework if it couldn't be used by all those languages? That's the reason it makes it worthwhile for us to invest in framework. It makes it worthwhile for you to invest in a framework, is that it's got very, very wide usage. So we need some way of not just making each language work, but of making each one able to use stuff produced by the other. So we wanted to have some way, if you write your program in C++ and you create some classes, and then you go to pick another language, C# or Scheme or Eiffel, whatever, and you decide you want to use that stuff, it shouldn't matter to you what language it was written in. So people ask, what language is your framework written in? And the answer is, what difference does it make to you? I mean, I could tell you the answer, but you have to ask yourself, why did you ask? It doesn't matter. What I wrote it in doesn't matter. You can use it from any language, right? That's been the goal, and the way you reach that goal is you create this thing called the Common Language Specification. It's really the guideline for the framework designers, but it also tells programming language designers things. And it's the rules that you need to follow if you want wide reach. So there's this common type system, and there are about 40 rules that say, well, that's the whole thing, but don't use the whole enchilada. Just use this piece of it, and then it's usable by all languages. So use this for anything you're doing inside, but what you expose to the external world, use this simpler, smaller set of things. And what we've done is we've made a commitment to that. All of the .NET frameworks, everything you can do in the .NET frameworks, you can do using that subset. And so every one of these 15 programming languages can get the full functionality of that framework. Now, I have to admit, there are some things in the framework that are easier to do if you do some of the other stuff as well. But every single bit of it is doable with what you got in that framework. And to convince ourselves of that, we worked with 15 or so different languages. We investigated them very carefully. Some of them Microsoft implemented, some of them researchers implemented, some of them ISVs have implemented. Some of them we just looked at and didn't actually get an implementation. Most of them are what we call CLS consumers. In fact, almost all are what we call consumers, which is to say they can use anything that's already been built. So they can use all of that framework. A smaller number, but still many of them, can extend that framework by defining new classes and defining new interfaces. And primarily the ones that can't are the ones that the language never had the notion of an interface or a class before. They never had that notion to begin with, so they don't have any way of extending just because the language didn't. Anyone that was object-oriented at all to begin with pretty much meets both of those criteria. So we think that's pretty good to have covered a full range of 15 languages there. What do you get out of that? To me, tremendously important. You get to choose the right tool for the job. There are things that, much as I love C++, there are things that are much better written in Visual Basic. And much as I respect Visual Basic, there are some things that I wouldn't dream of programming in that language. So covering that full range, we believe, is just absolutely essential. So to review the goals of the runtime, it's multiple languages, it's secure, it has mobile code, it's scalable from big web farms to small devices, or vice versa. It has the side-by-side versioning so that you can safely deploy shared components. Self-description throughout, so you get something in this framework and you can run a tool that tells you about it. You get a very, very rich framework with a consistent API. Gives you a simplified programming model across many of the things that you've been doing in the past. Very strong integrated tool support. And sort of the bottom line for you is productivity, simplicity, and reliability. So that's what we've been working on for 3 years. Pleased to say I think we've done all of that. Now I want to tell you about how that runtime is supported through the entire life cycle of a program. So we're going to start by looking at the design and compile time part. The key story there is the metadata story, the story about self-describing objects. It's the key to simplifying the whole programming model. Absolutely critical to that is the metadata is generated automatically. All of the compilers, all 15 of these languages, generate the metadata along with the code. The metadata is stored right in the same DLL or XC or whatever it is that they, OBJ, whatever it is that they produce. That's where the metadata is. It's not a separate file. You can't lose track of it. It's integrated directly in there. It uses the COF file format, which is a standardized file format which runs on all of our platforms, all the Unix platforms, other platforms as well. So it's a very standard, well-accepted file format. It was extensible in the beginning, and we used that extensibility just like we and other vendors have always used it, added a directory entry that we use for this purpose. It's stored in a binary format in that file. It's a compact format. It's designed to be compact and yet extremely easy to access. It's convertible to and from XML schema. We provide command line tools to do that. We also provide, it's sort of hidden in the tools. It's being automatically done for you in many cases. But it's fully interconvertible with the XML format that's used on the wire for this. And it's convertible to and from COM type libraries. So if you have an existing COM type library, you can just turn it into something that's in the metadata format and then use it. And similarly, if you write something and you want to expose it to the COM world, there's no extra steps. It's just done for you. What's in there? 3 big things inside the metadata. The first is the deployment unit, the assembly. And you'll hear a lot about assemblies here. There's a whole talk on assemblies and administration. They are, I think, an absolutely key concept in the system. They are the thing that you should be thinking about building and deploying as the primary reusable units. You could think of them as logical DLLs. That's not a name I particularly like, but that's one way to think about them. From the metadata point of view, really all it takes to make an assembly is to put this little thing called a manifest in the existing file. So if you've already got a DLL or a set of DLLs that you think should be shipped together to make one coherent whole, the way you do that is in one of them, you describe that collection. And the description is what it says right here. It's the identity of the assembly, the name. It has a logical name. It has a version number. It may or may not have a cultural particular version. So it may say this is the American English version or the French Canadian version or whatever, or it could say this has not yet been localized. Those are critical to the identity of the assembly. And in addition, optionally, you can provide a public key and a hash and say, whoever owns the private key that goes with this public key is the person who produced this assembly. And then later on at runtime, you can check whether you got an assembly that was produced by the same publisher. So there's no certificate here, it's just the key. Just make sure that you don't lose your private key and we'll all be fine. What types are exported from the assembly? So you've got this unit of files, and the question is, okay, what types are available if I were to load these? So that's the next thing you provide to tell me about your assembly. The third thing, and it's a critical one, and it's different from anything we've done in the past, is you also say what other assemblies are going to be needed if you're going to use this one. So we have all that dependency information. So you can write administrative tools that say, in order to run this application, the application needs these three assemblies. Go to the assembly, what does that assembly need? And just go and recursively do that tree and find out what's needed. Make sure it's all there. That's how things like, I can run this application offline work. Because they take the beginning of the application, and before they say they've got everything you need, they make sure that they have all the pieces that needs and all the pieces that needs and so on. That's how you make sure you've got everything you need. So that dependency information is critical. It also is, the assembly is also the security boundary of the system. And in two ways, I'm going to describe one of them now and one of them later, but one of the things you say about an assembly is, in order to run me, you must give me the following security permission. So for example, I've got this collection of DLLs, and in order to use them, they have to be able to read and write to the net. There's no point in starting and loading this assembly unless it has permission to do that. So we will check that first. And there are actually three things you get to say with your assembly. I must have this permission in order to run. I would like this permission, but if I don't get it, I'll run anyway. And I don't want this permission. Don't give it to me, because if you did and somebody misused me, things could go wrong. So we provide all three of those in the assembly. So that's what makes an assembly, is it describes itself, it says what it needs, it says all of the dependencies it has. That's an assembly. And that's all in the metadata. Another kind of metadata is the description of the types that are in there. The name of the type, whether it's visible outside the assembly, what its base or parent class is, what interfaces it implements, what's inside of it, its members, that is, its methods, its fields, its properties, its events, its nested types, and so forth. And the third, and we'll spend a minute on this one, is custom attributes. This is our extensibility mechanism. So it is possible, you've got this metadata that describes either the assembly or the type, and you can put on any of those descriptions your own custom information that can be used by compilers or tools to understand anything you like about that type or that field or that method or that assembly. You can define them yourself. Individual compilers can define them. The framework can define them. There's a fully extensible mechanism, and we're going to talk about why that's useful. But that's really one of the critical things about this, is not only do we have metadata, not only is it created automatically and transmitted with the files, but users can extend that themselves. So, sort of what's the value of all this metadata? Well, the general flow of controls, you start with your source program, you compile it, and if you're on the metadata team, you say, okay, and you get metadata. And if you're at the runtime team, you say, well, you get the metadata, you also get the code, right? So when you compile it, you get the metadata and the code for the program out, and they live together. And from that, I've only listed 7, 8 major services you get. There are others. The one in the upper right there, the reflection one, so that says at runtime, as you're running, you can ask what types are there on the machine. If you're used to programming in VB, this happened in VB. It's called late binding. I can ask what types are there. You can give me something that all I knew at the time I was compiled was that it was an object. I can ask what type of object. Given that I know what type of object, does it have a method called add on it? If it is, would you please call that method? So I didn't have to know which particular method of add I want. That's all done at runtime. I can also, with that same reflection service, say, I'd like to create a new type, please. And it has these methods, and here's the code for the methods. And now would you make me one of those objects and call this on it? So you can actually write the program at runtime, and you can save that out to the disk and use it in the future. And this is used by our interpreters, and it's used by some of our compilers. It's a really extensible way of doing things, all because you can write that metadata out yourself. The designers, we'll talk about that in a minute again, but all of the designers in Visual Studio work by looking at the metadata and looking for certain custom attributes that tell it where things should appear in the design frames and so forth. The debugger, how does it find out what the methods are? It looks at the metadata. The profiler for getting performance measurements, how does it know what the methods are? How does it know what fields there are? How does it know where in the file the code starts? All of that stuff's in the metadata. In that remoting story where I told you we automatically go from one machine to another, well, there's got to be an on-the-wire format. That, of course, is SOAP, which is the standard XML-based format. But there's something that's got to take this object in memory, which is just a big hunk of bits, and turn it into this almost textual description of those bits. And the way that works is at runtime you have this object, and you ask that object, what type are you? And you ask that type, what fields do you have? And that's exactly what you need to write out the SOAP format on the wire. So that's how serialization, either sending it to a remote place or sending it for storage in a file, that all works off the metadata. How does cross-language inheritance work? I compile it, I get metadata. I want to use it in a different language, I read that metadata. That metadata doesn't have anything to do with the programming language it was written in. So that's how cross-language inheritance works. Type browsers. I want to know what types I have. I look at the metadata. Schema generators, proxy generators, conversion to XML formats. That's all driven off of the metadata. Compilers use it, as I said, for this cross-language import, which is the basis for cross-language inheritance. They emit it directly with their output code. They record all the references. Remember, I mentioned the versioning information and the assembly dependencies. Those are all recorded automatically by the compiler. Custom attributes can be used for a bunch of different things. One of them, which before we released the bits to you, that class library was evolving pretty rapidly. And you wanted to tell all of your users that there's this method that's going to go away in 3 weeks. And you didn't want to have to go and rev 15 compilers so they knew that that was going obsolete. So what do? If you're in the frameworks team, you put a custom attribute on that method, and all the compilers, when they detect anybody calling it, they give a warning to the user saying that method's been marked obsolete. Right? So that's one use of the custom attributes. If you want to generate something that's usable across multiple languages, you need to be able to mark when you managed to meet that bar and when you didn't manage to meet that bar. And there's an attribute that says that. The compilers use it for telling the runtime, for example, if you compile something and compile it with a debug switch, they put a custom attribute in there on the assembly telling the runtime the goal was to make this debuggable. And so when you run that, remember there's that conversion from IL to native code. In that process, we will generate debuggable code. So the front-end compiler has to tell the runtime, make sure this is debuggable. And finally, there are language-specific markers. So C++, for example, has the notion of const. While it's a great idea, most other languages don't have it. So they put a custom attribute on the metadata. So other languages that know about const will know this parameter is supposed to be const. And other languages that don't. They can just ignore it. How do we use the metadata for the design time experience? Well, if you remember to those designers, there are these categories. The buttons are here, the pop-up menus are here, and so forth. You've written a new component. How do you tell the designer where it belongs? The answer is you put a custom attribute that says, this is in the button category. And then the designer will put your name up there in the buttons. And if you remember, as you move your mouse over those things, a little description pops up. How did that happen? Again, you put a custom attribute on your type saying, here's the descriptive information that ought to pop up in the designer. Also, the designer is fully extensible. So, you drag and drop a control down, and you double click on it to edit it. Well, what if you have a control in its editor you want to write? You have to tell our designer to call your editor. How do you do that? You put a custom attribute on your type saying its editor is that thing. And then the designer will just call your editor instead of ours. Web methods. If you saw the demos where you just put this little thing in the front that says web method, that's a custom attribute. That's showing you some language syntax for putting custom attributes in. That's all web method is. It's a custom attribute on a method saying this one ought to be exposed to the web. And then the tools look through your program after it's compiled for that attribute. And anything that has that attribute, it produces the appropriate XML for SOAP, and you're off and running. Right? Type viewers do the same thing. So that's the design and compile time part of our runtime. How about the deployment time? We've talked about assemblies. It's a little more detail. Remember, the assembly is the unit of deployment. This is a hard one. It's not a packaging technology. It's not like a CAB file. It's not like a zip file. It's not got anything to do with that. It's take an existing DLL, put a self-description inside of it so that people will understand that this DLL, that DLL, and these three resource files are supposed to go together. That's what an assembly is. And it has this thing called the manifest, which is what takes it from being a DLL to being an assembly, or an XE to being an assembly. It just means putting that metadata inside it. Assemblies are not only the unit of deployment, they're the unit of versioning. They have version numbers. Part of that self-description in the manifest is what version number this is. And compilers, when you try to use one, remember which one you used, which version you used. And then at runtime, or at deployment, well, not deployment time, but sort of at install time, actually, when your program runs and accesses that data, it tries to access that assembly, there is a policy that says, as part of this application trying to reference that assembly, always use the one that I saw at compile time, or always use the latest compatible version, or use the latest known good version. So it's on the assembly basis that that versioning happens. I talked about one half of the security stuff with assemblies before, which is assemblies say what permissions they require, but there's another half of it which is they are the things that are granted permissions. So they say what permissions they want, and then they are granted the permissions. And then any method in the system. So if you're writing a framework and you want to make that framework secure, you can say, in order to call this method, you have to have been given a certain permission. And then while the program runs, whoever tries to call you, we will check to see that they have that permission, and whoever called them had that permission, and so on. But the permissions are always on the assembly basis, so you don't actually check for every method. It's really every new assembly you see on the call stack, so it's actually relatively fast. But the security boundary really is the assembly, not the individual method, not the individual DLL anymore. Assemblies are also the thing that mediates type references. So if I want to reference a type, I have to remember the assembly and the name of the type within the assembly. That's what actually references a type. And if I'm in one assembly and I want to reference a type in another assembly, I always do it, of course, by the assembly name. So I go to that assembly, and that assembly has the right to say, I'm sorry, that type is not available to you. So there is an interaction between the assemblies to decide what types are being made available outside themselves. Now, today, and in the bits you have, the only thing you get to say is either it is or it isn't. But there's an extensibility point there in the future. You could say, make it available to that assembly, but not that assembly. It's all possible to do. The twin notion of the assembly, remember the assembly is the deployment unit. The application is a configuration unit. It's actually the administrative unit. It consists of one or more assemblies, as well as any application-specific data files that it has. So Word is an application, and it might be composed of many DLLs, which are assemblies, or many different assemblies. And it can share some assemblies with other applications on the machine. So the grid control, remember, is a nice example of a shared component. Right? When you go to look up an assembly, you ask both what's the name of the assembly and its version number and so forth, but also what application is trying to do the lookup. And based on those two things, you decide which assembly to get. So this application running and this application running can be asking for exactly the same assembly, but they will get different ones. This one might get an application private version of that assembly. This one might get the shared version of that assembly. And if I had a third one, it might get a shared version, but a different version of that same component. All of that can happen depending on how you configured the applications. Applications can have private versions of assemblies, and if that application goes to look for that assembly, it gets its private version always in preference to a shared version. If it's looking for a shared version, then it will have policy that says which version do you want? The one you were compiled against, the most recent compatible, the latest no good, and so forth. So that's all the application configuration information. What about at execution time, which is, of course, where most of us think that a runtime is? So here's the model of what happens in the system. You have some, what we call the front-end compilers. Those are your actual programming languages, Visual Basic, Visual C++, scripting languages. As I say, we have about 15 of them now between us and various partners. They all generate this intermediate language. And the normal path is that solid line. You take the intermediate language, it goes into the common language runtime, and then we provide you two compilers that go to native code. The EconoJIT compiler is the fast compiler. It runs really fast, and it generates not so good code. Right? But it's great if what you have is the case where you're going to download some code, it's fairly small, you want to run it once, throw it away. It's great for scripting, that kind of thing. Trade-off, we also have a regular JIT, which is the default, which is an optimizing compiler, but tuned to run as part of the runtime. And it generates very good quality code. It takes a little longer to do that compilation, but the compilation happens only once when you start up. And it doesn't happen when you start the application. It happens on the first time you call a method. So the first time you call a method, there's this hit to compile it to native code, and then it's running as native code from then on for the rest of that application's run. We also, and this is the little dotted line there, we provide another option. Sometimes you have code that you really know is going to be used quite often and needs to be well optimized, and you want your application to start up quickly. So in that case, we provide what we're calling install time code generation. When you install it, we will run that optimizing JIT compiler and compile it down to native code and lay out all the classes and lay out all the information. And then when you try to run the program, that was all install time. Now when you try to run the program, we will find that. We'll do some version checks to make sure that nothing changed since you compiled it. And as long as nothing significant has changed, we'll run that. Startup time is a snap. There's no class layout, and there's no JIT compilation. Why don't I do that all the time? First of all, if you're in download scenarios, that's going to take a while, and you don't want to do it because you don't need to persist it. You'd rather do it incrementally. Secondly, you're using up a fair amount of disk space to hold all those compiled images. Thirdly, if things do change, if you're in a dynamic environment like you're doing web hosting or something and components are changing all the time, or you're in a development environment and components are changing all the time, it would be wasted effort because by the time you got to run the thing you compiled, some component it needs has changed, and that thing is going to be thrown away and you're going to wind up JIT compiling anyway. So it's a trade-off. We offer all the options, and it's up to you to do the trading off. Oh, by the way, there's also native code, right? Stuff that was already compiled. It's got nothing to do with us. We call it unmanaged code. I'll get back to it in a minute. It plays a very important role in our system. What's the process model? So the operating system supplies us a process that gives hardware isolation. Within it, we have what we call application domains that give, if you use type-safe code, they give memory isolation within the process. If you're a hosting application like ASP+, and you know that the code that you're going to host is type-safe, and we'll talk about that in a minute, then you can safely run multiple application domains in the same process, and they can't interfere with one another. The application domain consists of the data about the classes that it uses and the native code needed after, after the IL to native code compilation, the code needed to implement that application. And threads go merrily along. Remember, it's a thread pool, so they start up, they do their work in this application domain, and then they go back to a thread pool, and when they come back out of the thread pool, they might be in another application domain. But for the life of the thread, it doesn't really go from one application domain to the other. It stays within, goes back to the pool, comes back the other place. This is a very nice model. It works very well for downloaded sorts of things. But there's a case where you have some code that has, you have one particular assembly, for example, that's going to be used in all of the applications or in most of the applications. And so rather than duplicate that code in every application domain, think of the definition of the string class. It's a fair amount of code to implement strings. Strings are the same in every application domain, right? So it'd be kind of crazy to just have it all this way where all the code is in every application domain. So we also allow you to share it. So you can make these shared types, and then their code is available in all the application domains. It's not copied in each application domain. And again, there's a trade-off. It turns out in order to do that, that code, while shared and therefore reducing your memory size dramatically, runs a tiny bit slower because it has to know which application domain it's running on behalf of in certain cases. So there's a trade-off there. Again, you can do both. We do both within our own code base. The notion of managed code, just so we're very clear about what it is. All the code that is running within the runtime is what we call managed, and it's a deal. And the deal goes like this. Managed code provides the metadata that describes the data. From that information, we can automatically derive where the object references are and an exception handling table. And if it provides those two items, then the runtime provides this whole host of services. It provides exception handling. It provides this advanced security system. It provides automatic lifetime management. It provides debugging. It provides profiling. It provides a whole raft of services. But the deal is you've got to give me the metadata and the exception handling information. And the general flow of control is like this. The primary unit is the assembly. You load it through the class loader. You try to call a method on it. That will cause that method to be compiled. So let me explain that in a little detail. You load this assembly. It has some types. Those types have some methods. Those methods have some bodies which are in IL code. IL code can't be run on the computer. So what does the class loader do? It allocates an address in memory for every one of those procedures, or every one of those methods. And at that location, it puts what we call a stub. It's a little bit of, on the x86, it's x86 code, whatever, native code. And that little piece of native code says, if you call me, compile me, and then run me. All right? So that's what happens when you load it. Then when you call the method, of course, it compiles it. And actually, before it runs it, it sort of smashes that stub and say, okay, fine, there's the code now. So the stub used to say, go here to compile it and run it. Now it goes over here and says, there's the code, go run it. So future references have no overhead. They will just go and run the code. And that's what we call managed native code. The output of that compilation process is managed native code. And it's just native code. It runs on the CPU directly like anything else would. Now, it calls out, just like any program today would, to this execution support system. So think of it like the C runtime or the COBOL runtime or the Fortran runtime. When it needs to do complicated things, the IL to native code compiler has put in calls to those execution support routines. And because it was done by a JIT compiler, the actual addresses of them are known, and its direct calls is very convenient and fast. It can also call the security system. So if you mark this method to say a certain permission is required, then the compilation of that program will have put in a call to the security system, say, does it have the permission, and if not, raise an exception. And the final thing is this thing called the code manager. Periodically, there's a separate thread that's running in this system deciding whether the memory needs to be compacted. And many garbage collections don't require it, but when you have to compact, this code manager comes in and asks, is it safe to do this right now? And if so, it goes ahead, and if not, it waits for a little bit, and there's a handshake there, and it goes ahead. So that's what the code manager is primarily about. Or if an exception is raised, so you divide by 0, the code manager gets called to say, okay, who wants to handle the divide by 0 exception? That's what the code manager is. Now, the sort of funny thing that happens here is if I'm running this program and I go and I call a method that hasn't been JITted yet, what happens? Well, let's see. There's still that stub from the loader. So that's what that line from the CPU back to the IL to native code compiler is. On the first call to a method, the stub that's there says, go call the compiler. Now, while you're compiling it, it's looking at all this IL code of what the method's supposed to do. It may find that that method needs to call on a method of a type, and the type hasn't been loaded yet. That's that next arrow. So if the compiler discovers the type isn't there, then the compiler will load the type. And of course, loading the type will create the stub so the address of the method is available so the compiler can then continue. So that's how the loop works. So we incrementally compile things. We only compile things when you first call them, and we only load classes when you first reference them. So the whole thing is incremental. I think I've actually covered everything on there. That was managed code, and I want to talk about managed data. If you take, the reason I want to make this big distinction is if you're a C++ programmer and you take your existing program, it's not using any managed data. It's not using any objects provided our object system. It's using C++'s internal structs and classes and that sort of thing. That's all unmanaged data. You can compile that all and you get managed code. There's no managed data. There's no garbage collection that happens. There's no marshalling that happens. It's all just C++. It's just been compiled to this intermediate language and run. Now, from C++, you can start experimenting with using managed data, or with languages like C# and VB, you are normally programming with managed data. What is managed data? It's data whose allocation and lifetime is managed by the runtime. So the layout of that data typically is left to the runtime. Typically, those languages simply say, I need a type which has 5 fields, 2 integers, a float, and an object of some kind. And at the time when you load the class, we look at that, we say, okay, the best way on this particular machine to lay that out is, this way in memory. But the compiler can also say things like, you're free to do it any way you want, but the order of the fields has to be this order. Or you can say the packing has to be this tight. Or you can go all the way and say, actually, I'm going to tell you the details of exactly how I want it laid out. This is all done by the compiler. Programmers in any language that I've seen don't do any of this. But that's sort of behind the scenes. The compiler says how it wants the layout done, and then the runtime obeys that layout. And then the second half is the having allocated memory. When you say new, the compiler generates code to actually allocate the memory, and that's part of the runtime. What happens there is every once in a while, we continue to allocate continuously for a while. We run low on memory, and then we do a garbage collection algorithm. It's quite a sophisticated one. It compacts your working set which in servers gives you a tremendous performance boost. It does move the data around, doesn't move all the data around, it moves only parts of the data around. It updates all the object references. And the interesting thing is the design goal is that in almost all cases, it's no more intrusive than a page fault. So that really is the best way to think about the impact of garbage collecting on your program is it's like page faults. In most cases, it happens about as often and it takes about as long. And how many of you, when you write your program, worry about where page faults happen? When I did this inside of Microsoft, I got one hand. It was somebody on the NT kernel team. Okay, right? Those are the people who have to worry about that, and they do. And in fact, if you are in that kind of case, you will have to worry about garbage collection, and there are ways of dealing with that. But in almost no case does it impact you, except that because your working set is being compacted for you automatically, your performance is improving over time. It's just weird. Take home those bits, play with them, see what you think of it. Another big piece of the system, remember I told you there was unmanaged code that was precompiled, Win32 DLLs, COM DLLs, existing code you've written that you don't want to rewrite. Can you use that? The answer is absolutely yes. It's one of the most important things of this system. There's a barrier there. You have to do work when you want to go from one side to the other. But it's not that painful. If all you want to do is go across the barrier, if the data types are identical on the two sides, then there is some work, but it's actually very small. If, as in any kind of programming environment, if you're calling a procedure that wants data in a different format than the format you've got it in, you've got to copy it. So you have to do data marshalling. That can be an expensive operation, but it depends completely on what data types you've chosen on the two sides of the boundary. All of the unmanaged data types are available inside of the managed environment, and if you use C++ on this it just works stuff, then it's the same on both sides, and there's no marshalling cost, there's just a boundary crossing cost. And the other thing you need to know, and there's a performance talk that I think is tomorrow that goes into a lot more detail on this, that compilation from IL to native code, it actually knows whether you've got managed code on both sides or whether you're crossing managed to unmanaged and whether you're marshalling data. And so unlike the traditional COM and DCOM world where when you marshal, there's at runtime, there's a little interpreter that sees what all, you built a call stack and there's a description of what you put on the call stack and the description of what you wanted on the call stack, and it kind of goes through and it mushes it all around to make it match, which is fairly slow. In many cases, what our JIT compiler will do is it'll say, oh, he's calling this with these three arguments in these formats, and you want these three arguments in different formats. We'll just take the first one, convert it, take the second, convert it, take the third, convert it. There's no munching around. There's no writing it one way, rewriting it the other. So you get a good performance improvement out of that kind of compilation technique. I don't think I'm even going to spend time on this, just other than to say that there are three ways of going across the boundary. And if you get the printed slides, you'll see this, and it's certainly in all the specifications with all the details. Well, let me spend a moment on COM interop, which is the most important case where this happens. COM interop uses a standard mechanism that gets you from the managed world to the unmanaged world and does data marshalling. That's the p-invoke mechanism. But in addition, it performs object identity. So if you have an ion known in the COM world and you pass it in, we will create an object for you. And if you pass us that same ion known again, we will give you the same object again. So that's object identity. If you pass that object out, we will create an ion known to pass out. And if you pass it out twice, we will pass out the same ion known. Selected interfaces like ion known, we just produce automatically. You don't have to write them at all. You just code it as a class, and we make the ion known for you. Any types that you define are automatically exported to COM, and they're registered. COM type libraries can be converted to metadata, and you can import them just like you could if they had been compiled by a managed language. And a lot of the COM types, not all of them, most of the OLE automation types, not 100% of them, but most of them, and there's a list in the specs of which ones, are marshaled automatically. So it makes the work very easy for you. You just write the code, call it, and all the marshaling is done for you. There's no plumbing. You don't have to write that marshaling code yourself. So just to summarize this whole thing, our goal has been to have simpler development, deployment, and administration. Those are the main goals. We want multi-language, secure mobile code. A thing to just take away and remember about this is all code is compiled before execution. It's not a traditional virtual machine. Full interoperation with your existing unmanaged code, and truly scalable all the way from smart devices up to web farms. It's a strong foundation to build on. A little bit about related sessions, and let me take questions. How many minutes do we have left? None?
We pretty much have about 5 minutes.
Oh, so we have about 5 minutes. So I can take a few questions, and I'll certainly stay outside and you can ask me questions later. Any questions here? We have microphones.
Yeah, I have a quick question for you.
Yeah.
I'm on your right side.
Thank you. Somewhere.
Nice session. What's the size of the runtime?
I don't know offhand. Look at the CD.
Okay. Thank you.
Sorry. Yes.
I still have some concerns on with regards to performance. How come we're not going to have the same performance issues that you do with Java? I mean, all of a sudden now it seems like everything is almost interpreted.
There's no interpretation.
Well, it's kind of like VB had P code, and the P code would get compiled, right? No?
It's far better performance. Measure it for yourself. Go to the perf talk. This compiler, our measurements, if you compare against VC 6.0, native 6.0, the current native code compiler, to our current JIT code, they are often within 5% of that performance, often less than that. There are notable cases where we are worse, but we are very close to the native code performance. The third-party compilers are confirming they're seeing similar results for many of the languages, that we are within 5% to 10%, 5% often, of their native code performance.
Well,
We've had 3 years to do nothing but work on this.
My question relates to the same thing, basically the native, the IL to native compiler. Correct me if I'm wrong. That's going to be part of the operating system then, the compiler?
That is part of the common language runtime. So wherever we are installed.
Okay. Well, that becomes a big issue then in terms of I kind of see DLL hell being replaced by versioning issues with the compiler then. Different behavior perhaps on different clients' machines based on which compiler?
We have side-by-side operation of the common language runtime itself. So you can take a version dependence on the runtime, upgrade it, and maintain the same previous version if that's what you'd like to do. And of course, we're going to work mighty hard to make sure that as long as you're sticking to our JIT compiler, there's not, every compiler says this, right? But
sure.
We mean it this time.
So basically, are you going to support multiple versions of the JIT compiler then on a particular?
Multiple versions. The JIT compiler is strongly and completely tied to the version of the runtime. So the runtime contains the JIT compiler. The whole runtime has a version. So you can't update just the compiler. You will update the runtime and the compiler in sync.
And that gets installed on the client's machine then, basically?
That is
on the customer's machine?
That's correct.
Okay.
And there will be a redist that includes all of that.
Thanks.
When the class loader is loading the assemblies, how does it locate the assemblies?
That is exactly the content of the talk on administration and deployment. So I'd rather not answer it here. And if that talk is already over, come and talk to me. But there's a full hour on that, so I just can't give a short answer. The largest single answer is we have a cache where we keep them, and that you explicitly install into or choose not to. And if it's not in that cache, then it appeals back to the host, to whoever started the runtime, to find it.
One more.
One
more question. Also, it looks like you've totally replaced.
I'm sorry, I've been told we're out of time, so I'll just meet you right outside the doors there. Thanks.